firstly, we'll be going over a quick introduction as to what AWS EFS is, accessing EFS from a Kubernetes cluster, internals of the EFS CSI driver. And from there on, Priya would be taking on for static provisioning and dynamic provisioning in the AWS EFS CSI driver, a quick demo, and some troubleshooting tips. Yeah. So what is AWS EFS? Elastic File System is a completely managed, highly scalable, and a serverless NFS-backed offering by AWS. So it grows and shrinks automatically as you keep adding and removing files from it. It can scale up to petabytes of storage without any application disruption. And it also supports encryption of data at rest and in transit. So in short, to put it all in a line, it is an NFS with some cloud flexibility. So coming to EFS access points. So these are application-specific entry points into the EFS. We can enforce user identity using POSIX groups. We can also enforce root directory for different clients. What it basically means is that we could be sharing just a part of the EFS without having to share the entire EFS with a client. So basically, let's say you want to share just the SRC folder of this entire file system. You could very well do that using an access point. So moving on to the next slide. Yeah, so this is how a typical page looks like when you want to create an access point. So firstly, you have to, provide the file system to which you want to create an access point. The name is optional. The root part directory is also optional if not given defaults to a slash. But in this case, since we want to share the SRC directory, we would be saying the root part directory to be /src. As I told, we could also enforce user identity. So the POSIX user ID, group ID, and so on could be given. We can also configure what permissions you want the user to have on those directories. So once created, an access point would look something like this. It would have an access point ID, the root directory path, which if provided, the POSIX user, and even the creation info, like what permissions does the user have on this directory, and the status of this access point. So yeah, coming to the file system policy, just like any other service in AWS, even EFS has a file system policy. And if a file system policy is not present for EFS, it basically means that it is accessible anonymously. So what it means is that any entity which is not identified as a user, group, or a role by AWS will still be able to access your EFS. So now, once the EFS policy is in place, it enables IAM authentication and authorization for your EFS. So, and also the Kubernetes pods will now have to use a mount option called IAM to be able to mount the EFS to the Kubernetes pods. So what it means is that as long as this AWS role, which is being used by the EC2 instance, is available in the file system policy of this EFS, this EC2 instance will get access to this file system. So yeah, I will also be showing a sample policy. Looks like any other policy in an IAM. So firstly, we have a principal. As I told you, we have to add the IAM role of that EC2 instance. It would be added here. So it would say who has access to this file system. The action basically talks about the operations that are allowed by this user on the EFS. And all of this will hold true when this condition, that is the file system is being accessed via a mount target, is true. So only when the file system is being accessed via a mount target, all of this would hold true. Yeah, so that is what file system policy is all about. Yeah, so now accessing AWS EFS from a Kubernetes cluster. So traditionally, we used to use a EFS provisioner to be able to mount EFS onto Kubernetes pods. It would do so by creating a subdirectory in the EFS and mounting that subdirectory to the particular pod. But it came with a lot of limitations. It got deprecated late in 2020. It was a legacy solution and it had stopped being maintaining. It had a lot of bugs and we could not use EFS to its fullest extent. So what was this way out is to use a CSI driver. Yeah. So what are CSI drivers? So CSI drivers are a standard for exposing arbitrary block and file storage systems uh, to container workloads running on container orchestrators like Kubernetes, Mesos, Docker Swarm, etc. So why did we need them when we had something like a Kubernetes EFS provisioner? So the thing is, the EFS provisioner that I spoke about in the last slide is limited to Kubernetes. So if you wanted to expose EFS to any other container workload, or being run on any other container orchestrator, you would have to use its own provisioner. Like if Mesos, if it was Mesos, Mesos would have its own spec to expose EFS. Docker Swarm would have its own spec to expose EFS and so on. So the storage vendors found it very hard to be found it extremely hard to be implementing so many of these specs just for their storage solution to be able to talk to different container orchestrators. So all of these container orchestrators came together and decided upon a standard which had to be, came upon and decided upon a standard which once implemented would be able to be used by all of the container orchestrators. This standard today is the CSI standard, and it essentially has around 20 functions in it, which once implemented, one could say that we have implemented a CSI driver. Yeah. So what is the EFS CSI driver? So the EFS CSI driver is the CSI implementation for the lifecycle management of EFS in a containerized workload. EFS CSI drivers today support both dynamic and static provisioning. And yeah, so these are the following functions that have been implemented in the CSI driver. These are around 13 odd functions of the 20 which have been given in the CSI spec. Around 7 of them have been implemented as no ops in the EFS CSI driver implementation. So I'll be talking about how a CSI driver is being set up in a Kubernetes cluster. So the containers in green are the CSI implementations. That is the node service and the identity service, which run as a daemon set. So the node service will have to run on every node of the Kubernetes cluster, which is why it runs as a daemon set. While the controller node runs on one or multiple nodes, depending upon the failure backup that we need. So, but what we have to make sure is that if we have multiple controllers deployed, we should have a mechanism of selecting the leader, and also make sure that only one controller is active at any given point in time. So we also have the sidecar containers, which are in pink. These are the sidecar containers provided by the Kubernetes team. So now, why do we need these sidecar containers, right? So when a CSI driver is implemented, none of the core Kubernetes code, or for that matter, any container orchestrator code is being touched. So we cannot expect CSI drivers to right out of the box be able to talk to the Kubernetes API server. So to facilitate that, the CSI drivers are provided with the sidecar containers by the Kubernetes team, which has external attacher, provisioner, detacher, and so on, which would help the CSI driver to talk to the API server. So if you look at it, look here, the controller service doesn't directly talk to the API server, but it uses this sidecar containers provided by the Kubernetes team to be able to talk to the API server. So this is typically how a CSI driver is set up in a Kubernetes cluster. Yeah. So coming to some of the features of the EFS CSI driver. The EFS CSI driver by default enables encryption of data in transit. So how it does is that it takes the help of the EFS mount helper. So this EFS mount helper would create a external process, and this external process would be listening on a local port between 20049 and 21049. And this external process would go ahead and create a secure tunnel between that local port and the EFS at the port 2049 of the EFS. So now any NFS client that is incoming would get redirected to that external client process. And this external client process would in turn communicate with the EFS securely via the secure tunnel which it has opened up. So this is how the CSI driver enables data encryption of data in transit. So another important feature is the support for the no reserve port mount option. So what it essentially does is to have a uninterrupted connection to the EFS. So let's say that we have a NFS client which is connected to the EFS, and for some reason this connection is lost. And this NFS client is not able to reconnect to the EFS at the same port. At this point, what the no reserve port option would do for you is to open up a new unreserved port at which this NFS client can connect for the time being to make sure that there are no disruptions to the application. And once the older port is ready for connections again, it would connect it back to that older port. So this is how the no reserve port support makes sure that you have uninterrupted connectivity to your EFS. So from now, Priya would be diving us deep into the EFS CSI driver.
So, hello everyone, I'm Priya Sehgal and I'll be talking. Am I audible in the first place?
Yes.
Okay, thanks. So I'll be talking about EFS CSI driver in action. So here we look at how it is used in the Kubernetes world. So before I start, just a quick recap on static and dynamic provisioning. So static provisioning, as you guys must be knowing, is a technique in which the admin has to provision the storage, which is nothing but EFS in our case. He also has to create a persistent volume object, or objects which they want to use, for which they want to use the storage. And then a PVC file is created which references this persistent volume, and it will be binded only if things like its access mode and size and other things match. And whenever the pod tries to reference this PVC, that's the time when this binding happens. But this persistent volume in case of EFS is nothing but the access point which Avnish showed, and that also has to be created manually. In the contrary, in case of dynamic provisioning, what happens is you just need to provision the storage. The admin needs to create the file system and has to create a storage class for that for the storage. The storage class definition file is nothing but it tells you what class of storage it is. So this file will have different parameters and will change depending upon the type of storage. Like if you have EFS versus EBS, or for Azure file storage, it will be different because the parameters are different. Now, what happens is that the admin doesn't have to create a PV, but there is a PVC file which is referencing this storage class, that it needs storage from the storage, and so it references the storage class. So when a pod references this PVC, that's the time when the request goes to the storage class and it provisions a persistent volume, a volume on the storage, and that is provided in this and the persistent volume object is created, and then the claim actually binds to this persistent volume and it is used. So here in this case, in dynamic provisioning, the persistent volume, that is the access point, is created on the fly when the persistent volume request, PVC request, like binding request comes in. So as I said, in case of dynamic provisioning, the storage class definition file is little not complex, but has a lot of parameters. So these are the various parameters with which the storage class has to be created. One is that you have to provide the file system ID, the directory permissions, and the UID GID, which Avnish talked about, the RWX, and who is the user and group. The base path. So here the base path is by default /, which is the root directory. However, if you want your access point directories to be created under a specific path, like for example, /home, then you need to provide that. We'll talk about subpath pattern and unique directory in a bit. Mount options is the mount option. There are multiple mount options, but like TLS is one, which is by default enabled. IAM is the other one, which allows you for IAM authorization. So whatever role is binded with your EKS cluster and the node, that IAM role will be passed on with the mount request so that EFS will authorize it. If you do not pass any IAM role, means you're trying to access the file system anonymously, and that will only be allowed if the file system doesn't have any policy applied to it. So now coming on to the subpath pattern and ensure unique directory. So what happens is that whenever you have a PVC and then a PV request generated and the access point has to be created, there has to be a physical folder, a subdirectory, like as Avnish had shown in his diagram, to be created for that PV. And that folder's naming convention was, if once the subpath pattern was not there, used to be same as the name generated for the PV. So if your PV name was say PVC 123, the folder's name will also be PVC 123. And there were a lot of discussion in the community wherein they wanted to have more control on the naming of the directory. Like, for example, you are hosting this for a MySQL server. They would want the directory to look to be with the name MySQL or something like that. So that's why how the subpath pattern came into existence. So this parameter, what happens is that when you provide this parameter subpath pattern and you provide the ensure unique directory as true, then what happens is that the name of the root directory which is created for the access point is created with the same name as whatever is provided in the subpath pattern. So in my case, when I was saying MySQL, it's created with the name MySQL plus some UUID is appended to it. Why? Because ensure unique directory is set to true. However, if I set the ensure unique directory to false and provide a subpath pattern, then what happens is that the subpath pattern is only used for creating or the same directory, if it exists, is reused. So a new directory is not created. So ensure unique directory sort of when it is false and subpath pattern is provided, this actually helps you in using a common directory, data directory in EFS, sharing that directory across namespaces or clusters. So you must be knowing that the PVC cannot be shared across namespaces, right? So for that, this is useful for that use case. The second use case is it's like, if you were using EFS provisioner in the first place for provisioning the EFS volumes, and now you want to migrate to EFS CSI driver. So there is no need to actually explicitly copying your data from one file system to the other or from one directory to another access point and so on and so forth. You simply go and look what actual directory has been created by the EFS provisioner and give that in the subpath pattern and give ensure unique directory is false. And suddenly you'll see that your new data is available in the in your to the CSI driver to your pods. So now we'll quickly go through the definition of these files and I'll show you a quick demo. So here on the left side, I have the storage class definition for my for doing the dynamic provisioning, and the name is dynamic primary. The provisioner is this. My access point mode is provisioning mode is EFS AP, means access points will be created. The file system ID is provided with whatever is already created by the admin. UID, GID, if it is not provided, then it takes it as root. The directory permissions and the mount options are optional. If I have provided -IAM, then the IAM role will be passed on with the mount request. Otherwise, it will not. Here, subpath pattern, I'm setting it to this value and the unique directory is true, which means my access point directory, root directory will have this name and append some random character, which we'll see. The PVC file is pretty simple. It just references this storage class file. And the pod definition simply references my PVC file, that is PVC dynamic primary, and the PV will be mounted on /data. And this pod of mine is pretty simple. It simply installs CentOS and does some things. So here I have a file system which I have created. I will be, if you see that the file system policy and access points are null, I copy the file system ID and have saved this in this storage class definition file. This is the subpath pattern, ensure directory true. So I apply this particular storage class file and then also the YAML for PVC and the pod. And we'll see that the pod is starts running, and we'll go and take a look at the access point page again. So now an access point is created. If you see that this access point is using the subpath pattern directory, and towards the end, there is some unique characters because the ensure unique directory was true. So now what I'm going to do is that I'm going to exec into this pod of mine primary, and there we'll see how the EFS is mounted. So EFS mount is available on /data, and it is mounted from 127.0.0.1 on localhost. And as Avanish had told that, the file system is mounted on the local host in the EFS CSI node, which will take a deeper look. And it is mounted on localhost some port where the external has bound. So that is where the call is going through. But on the pod, it looks like this. So now I had created this pod with the user and run as user 1000 and 3000. So I am going to now write into this /data. I'm going to create a file 1, and then we'll see the permissions of that file 1. So here the file is getting created in /data. So now if you look at the permissions, it is 1000 and 3000. And we simply cat the file and the file is available. So this was so this pod was available in some namespace 1. Now what we'll do is we'll copy this exact directory and we'll copy it to our subpath pattern and set ensure directory to false, if you see, right? So what I'm going to do is now I'm going to create another storage class and called as dynamic secondary. And we will create another PVC and pod in the secondary, like some other namespace. And there we'll see that, so here I created this pod called EFS app dynamic secondary in the another namespace. And we exit into the pod and the same, the storage class I had defined, right, was using the same directory. So here the slash data, we see that it is mounted. And when I look into the slash data, I see my file 1. So I can even create another file because this user also had permissions. This pod had permissions to read right into this slash data. So I create another file and both the files are created. Now, if we go to the access point page, we'll see that there are 2 access points because this was a second PVC which was created and PV created. But if you see that the paths are the same, which means the underlying directory is the same, that is why we were able to see the same data. But the access point ID is different because there was another PV created. Now what I'll do is that there are daemon sets, as Avnish told, right? EFS CSI node runs as a daemon set on each of the nodes, right? And that enables you to mount your file system using STunnel and everything. So there are 5 nodes in my cluster and there are 2 controllers running as HA this thing. So here we will be going to one of the EFS CSI nodes and executing into it and seeing what all things are mounted. So you will see a lot of mounts happening. And here you'll see 127.0.1 mounted to some Kubernetes location volume. So which means that this Kubernetes pod is able to access this particular EFS file system. Now, and this is because there were a lot of pods running. So now what we'll do is that if suppose you're facing some problem and you want to see that what's going on. So what you should do is you have to go to a mount.log file and that gives you all the logs of the mount request which have come to the EFS CSI node. So here if you see in the EFS CSI node, for one mount request, there was a TLS connection which was being established. A external got created, process got created with this PID. It started the mount and the mount was happening on this particular pod, for this particular pod, so on this PVC. And here, this is the access point, which is actually mounted. It's not the entire file system. So if you see the access points are different across the different requests. And this particular external is locally bounded to 20350. And similarly, it is bounded to some other port, in the range which Avnish told. So if you are facing some issues, you can very well go here and look as to what has gone wrong. So this was one demo. Then I have another demo wherein, I show the file system, where I show the thing about the IAM role, the file system policy, So here, my earlier file system did not have any policy, but now I have added a policy with IAM roles and actions. These IAM roles are allowed access to the file system. Now what we'll do is first, I had deleted the storage class in the pods. Now from the secondary namespace, I again try to create a PVC and pod, which is accessing this secondary namespace with the same directory. However, this pod will never get created and it fails with the access denied error, if you see, right? This is because we never passed the IAM option on the mount option. Now I create the storage class with the mount option is -IAM, if you see here, and again create the PVC and the pods in the demo namespace too. And this pod gets going, it starts running. And if we go into the pod and we see that, the same data directory is available and the files are actually available. So this was the demo with, with the policy and without the file system policy. Now, moving ahead, I think we have already seen in the demo, but just quick troubleshooting steps, which I was saying that if you are facing problems in mounting your EFS CSI, CSI driver, then you can look at the logs of the daemon set, or if you know which pod is facing a problem, you see that pod, which node that pod is running, look at the CSI node on that pod and look at the mount logs of that particular pod, CSI node pod, and you'll get you'll get some hint into what's going on. So this was all about dynamic provisioning. Static provisioning is pretty simple. As I said, you simply have to create a access point and provide that access point and file system ID in the volume file handle for this persistent volume definition. So because it is static provisioning, you have to provide a persistent volume definition also. The storage class definition is pretty simple. Then you have the persistent volume claim, which is referencing this persistent volume, and the deployment is using this claim. So this will simply use this. The only addition is you create a persistent volume with the access point ID, file system ID and the access point ID. So that's pretty much it from my side. These are the references. You can reach out to me and Avanish on our LinkedIn thing, and we are happy to take any questions. Thank you.
Yeah, thank you, everyone. We can take any questions if there are.
Correct me if I'm wrong. It seems like they moved from a legacy solution EFS provisioner to the CSI driver. Apart from providing the new features that the cloud platform provides, are there any performance benefits or anything? Any reasons for moving from, let's say, a EFS provisioner to a CSI driver?
So the main the main reason was that the EFS provisioner had stopped being maintained. It was deprecated long back in late 2020. And the CSI driver is mostly a solution for the storage providers. It is today a standard, and I think it's the industry practice to move back to CSI drivers instead of the EFS provisioners. So performance-wise, I'm not sure. I have to check and get back to you on that.
Thank you.
More of the security features also got integrated in CSI driver approach, which was not done or was difficult to implement with provisioners, EFS provisioners.
Right. So the IAM mount option, the TLS mount option, a lot of these mount options were not available when we were using the EFS provisioner. But with the usage of CSI drivers, we can use all of the features of EFS. Yeah. So data in transit, it lacks support for data in transit, IAM authorization, and even the no reserve port. So a lot of features of EFS itself weren't supported by the EFS provisioner.
Hey, Avnish, I have a quick question. That is, with EFS CSI drivers, there's a very known issue with when you try to provision something, PVC for a Postgres database, the UID does not get assigned automatically because Postgres expects a certain UID, and then for some reason, EFS CSI driver is unable to provision dynamically the user IDs based on that. So do you have any workarounds for it? Because I see there's the issue in GitHub is still open. It's not closed yet. So how do you folks circumvent that?
So to understand your question correctly, you're saying that if your process is trying to use a specific UID GID, the access point doesn't get created with that UID GID, doesn't entertain that? Is that okay?
Yes. So when you try to create a Postgres database, an underlying thing, so Postgres, it tries to create a user, I think 1001 and 1010 or something of that sort. And the EFS CSI driver is unable to assign that user. And because of that, the Postgres DB does not work. So you have to statically assign that URL for it to work.
Yeah, so you have to assign that using this access, the storage class definition, the UID and GID.
Right.
So in our case, like in Grafana, we have a case like in Grafana, we use this. And Grafana also has to be used with, I think, 476, if I'm not wrong, or 473 UID GID. So in the storage class definition, we had to explicitly give that UID GID. Only then it was honoring it, otherwise not.
Okay, so in our case, how we circumvent that was we create a different storage class for this, and so Postgres can handle and create PVC from there. And so is that the only way around, or can we have?
That is the only way. That is the only way which we know of, and that's what we have. Like if we have multiple like applications or whatever pods with different with access points which need to have a different UID GID, we have to create storage classes for each one of them separately with a different UID GID. Yes, that's how even we have done. There is no other way that automatically it will pick it up.
Okay. Well, then yeah, in a way,
There
it
is the workaround. Yeah, that's the only workaround. Yeah, yeah.
Phil, Prashant this side. So what's your use case with the EFS CSI driver plus Postgres?
So in Reliance, we have a Harbor instance that is our Docker registry and service that we use. So this has Postgres and all the other Harbor pods running. So Postgres is internal database. So yeah, because of this, we were using Postgres. I mean, Harbor, we were trying to run it on EKS cluster with EFS, and there we were using EFS CSI driver.
Okay, okay, thank you.
One question from my end. When AWS is offering other storage classes like EBS, GP2, GP3, is there a compelling reason why the team is using EFS? Any experiences on that will help to give the insight to all the audience, I believe. Thank you.
So Avnish, you want to take that up or I'll take it up?
Can you come again with your question? So
See, AWS offers other storage classes like EBS,
storage,
GP2,
EB,
GP3. A
S3.
lot of storage classes are there. Any compelling reason why you went for EFS?
why we use
So-
EFS in
There are so
our
many
product?
other storage classes also, right? So
Okay, so why do we use EFS is because we have a hierarchy of file that we store in our CD platform that we use. But
Yes.
yeah,
Avnish,
so that is one of the reasons.
So actually the main reason is that we wanted to share data across the different nodes and pods. That is not possible using EBS as such, right? Because EBS is only, you can share it, the data only if the pods come up on the same node. It's local. Whereas in EFS, it's like a very generic thing. Wherever you require NFS or file sharing support, that's the place where we'll use EFS. So in our scenario, we wanted the support that, like for example, we have Airflow pods running and they are scaling on multiple nodes. So there we will have to share the DAGs or DAG directory, for example. So that's the place where we require EFS, for example.
actually, if the microservice is able to replicate the data, you don't will probably not need this.
Yeah, so that that's true, you can replicate the data, but we didn't want to replicate a lot of data because there is a lot of data which is there and we didn't want to replicate all of it. That's why the sharing. So there are pros and cons, of course, that whether you want to copy the data and keep it along or you want to share it via file system. So it is a the block storage versus file sharing, that comparison, and that is a very generic thing, not just going to EBS or EFS as such. So we had that use case for sharing. That's why we used it.
Thank you for
Also-
sharing your use case. Thank you. Appreciate it.
Also, here in Cloudera, we like in Reliance team, we have nodes that are running across availability zones. So this EBS volumes cannot be shared across availability zones in general. So we use EFS so that nodes can use the same PVC and then deploy it. So even because we have that for fault tolerance reasons, and that's where we also use EFS.
Considering you have like one access point being created for every PVC, do the access points immediately get deleted in AWS after the PVC is reclaimed, or how do you know how to like clear out those access points after the lifecycle of?
Access points are immediately cleared off when the PVC is unbound and the clearing up happens automatically.
By the driver?
Yeah, by the driver.
Got it.
The directory is not deleted, the data still remains.
EFS is still there, the data is still there, but the access point as such gets deleted.
With that, thank you so much, Avnish and Priya, for the insightful, knowledge and the presentation about it. You guys feel free to reach out to them directly over the LinkedIn, or we have a page, Future of Data Bangalore. In that, this meetup is there. You can write your questions over there. You will get the answer.
Thank you, everyone. Thank you so much.
Thank you, everyone.
Now, our next speaker is Harsh. He will present the talk.
Good morning, everybody. Thanks for coming on Saturday. And first of all, I want to introduce myself. I'm Harsh Bhardwaj, and I'm currently working as SG2 at Cloudera. And I'm an SRE team, and I basically manage system uptimes, managing the infrastructure, and automating everything that we can to make the workflow more smooth. So today's topic is very interesting, and I hope most of you have worked in Kubernetes, or some of you have idea about cluster autoscaler. So today's topic is basically auto scaling via Carpenter. We'll be using Carpenter to scale, optimize, and upgrade your Kubernetes. So, so very important to know, why do we scale and why do we need even scaling, right? Because our end goal is to reach from here to here. So if you have workloads scheduled on pods, right? So if you're a small organization, you can use EC2 instance to schedule your workloads, but it's not practical. If you are a big company, big enterprise company, like at Cloudera, we have multiple clusters, 30, 40 clusters running, more than that even. So we need some scaling solution. So if you have to hire a person even to go manually scale the nodes, even if you use EKS cluster, you have to go and scale the nodes manually. So cluster autoscaler basically do that for you. So we use a lot of option for auto scaling. We have vertical auto scaling, horizontal auto scaling. So here we previously were using cluster autoscaler, and now we have moved to Carpenter. And Carpenter is a better autoscaling solution. I'll tell you multiple reasons for that. But this is the major thing we want to achieve. We want to have a solution which scales fast, scales down even faster, and helps to do many things that you are doing manually before. Now, this is the interesting example. It will tell you how basically Carpenter and Autoscaler, the major difference is. So you have a workload running, right? You have a workload, you have an EC2 instance or EKS cluster setup, and you're running your workloads fine on it. You have even HPA setup, pods are scaling horizontally, but there will come a time when it will stop scaling because the nodes are not yet available. So what it will do, the pods will get into pending stage, right? Your pods will stop scaling. Now, the pending pods will contact Kube Scheduler, which is native Kubernetes feature, and it will then trigger cluster autoscaler. And cluster autoscaler will trigger autoscaling group, and it will trigger EC2 API, which is EC2 Fleet. EC2 Fleet is basically AWS service, which is used to spin up multiple instances at a single time. So this is the whole workflow looks like. But now, do you see the problem here? Now, suppose I'm running my cluster, and now my company has introduced new GPU-based workloads. Now, how will I scale it? Currently, I'm running R6 medium and T2 medium, and I don't have capacity to scale GPU-based instances. Now, what I will do, if I'm using cluster autoscaler, I will go here, I will use Terraform, I will create a node group, I have to manage the Terraform, I will do tagging things, I have to configure node group with cluster autoscaler, then it will, GPU-based workload will be scheduled on the node, right? It will do all sort of things. But what Carpenter does, pending pods will directly contact Kube Scheduler, and that will contact Carpenter, and it will directly talk to EC2 API. So you skip all these steps, manually configuring node groups, patching the node groups, maintaining one more resource. So you saved all that by Carpenter. And Carpenter have two specific resources which does that for you. Node pool, which was previously known as provisioner, EC2 node class, which was previously known as AWS node template. So if you see, these both are YAML files. So that was what I'm talking about. What is Carpenter? Carpenter is basically Kubernetes native auto scaling tool, which is much more faster, much more scalable, and provides you a lot of functionalities apart from just scaling. So this is the basic difference. You save a lot of things. You don't have to work with node groups. Carpenter doesn't work with node groups. It is independent of node groups. So you can have a single node group running for Carpenter pods, and apart from that, all your workloads will be running on nodes deployed via Carpenter. And due to it, you are saved from patching node groups, meeting the Terraform. It's used in multiple things. You can do cost optimization. I will talk about it. It has consolidation concept, which you use, supports all type of workloads, and helps you patching and upgrading your clusters. Now, coming to the first file for generating Carpenter configurations, it's node pool. So what is node pool? We have two files, right? EC2 node class and node pool. Here's the top. We'll talk about node pools. So the node pools defines the type of configuration that you're going to use in the cluster. So for example, topological spread. You can use availability zones, like it will deploy your workload collectively, evenly across multiple availability zones. You can even define the instance type families. You can define C5, M5, R5, and it will only deploy your clusters from these families. Even you can specify the type of instance you want, size, nano, micro, small. And you know the superpower of Carpenter is, if you remove this, it will automatically select the best instance type for you. If your cluster does not need any of this instance type and you don't define this, it will, for example, need T2 instance type. So automatically Carpenter will deploy T2 medium instance type for you if you remove this thing. So this is also a very good feature. Apart from that, there's a concept called limits. Uh, how limits works, limit basically is a maximum threshold that you can use. So you can be sure that your cluster is not over provisioned. Some patchy application has come. So you can be sure your cluster is not auto scaled. Another thing, you can select the architecture type, whether you want to use AMD or ARM. It's an important feature depending on the application. And another feature is whether you want to use spot or on-demand instance types. Now you might be wondering, what about my reserved instance type? Don't worry. If you don't provide any of this configuration, it will automatically first go for reserve instance type. And when the reserve instance type is exhausted, it will go for spot and on-demand instance type. So you can be sure that your saving plans, whatever reservations you have buyed, are protected. Now the different type of node pools, I've already talked about single. Multiple means you have multiple files of the node pools. The weighted concept is really interesting. So as I talk about the reservation instance, how in practicality you will define that. So for example, we have two node pool files. And first of all, I've not defined anything in both of them. So first of all, I've given the weight, 60% of weight and 40% on-demand or spot types. So first of all, it will look for your reserve instances. It will exhaust that. And after that only, you will go for on-demand or spot instance. And you can see the YAML as well. YAML is similar to deployment, daemon sets, whatever you deploy via Kubernetes. It's a YAML file. Second thing I want to talk about is EC2 node class, which is the second concept for Carpenter. And as the name suggests, it is mostly based on EC2 configuration. So you can have your subnet selectors, security group, AMIs, and many more things. So what at Cloudera we did, we are not basically giving manually this subnet IDs or security groups or AMIs. We have auto discovered it. So we have all the tagging placed in the Terraform resources. So even if you tomorrow create new subnet, the Carpenter file will automatically detect it because we have auto discovery tags in place. So we will be sure every time that our networking and security constraints are protected and we don't pose a security issue. AMI I will talk about later, like how you can upgrade your AMI, because AMI upgradation is very important feature of a carpenter, and you will see how fast it is in comparison to your regular node group, sorry. So as I discussed earlier, it is very Kubernetes native and it supports all those native Kubernetes features. You can use topological spread, as I mentioned earlier, availability zones. You can use taint and toleration directly. You can use node affinity, you can use node selector, and it will work seamlessly. I'm going to give you an example how easy it is to maintain YAML file for it. It suppose all these labels. So when you deploy a node will have all these label predefined. You don't have to put your own label if you can actually, but I think these labels are sufficient to have any specific constraints. So for example, a use case for having a YAML file, don't have to configure any other thing. So if you see, we have already have label selected here. We already put the labels here. And now what if I want an application to only spin spot instance? It's a very important use case. For example, if you have any cron jobs or if you have any batch jobs that you only want to run on spot instance, why you want to spin up a reserve instance for it when you can run it for 5 minutes, shut the cluster and move on. So this is the very important thing. I've used node affinity for it. Uh, it will only schedule if if it sees the label. So it will not be spinning up on EKS manage nodes because it doesn't have this carpenter label. So you can be sure every time that your workload is always spin up on carpenter nodes deployed via carpenter, and it is always spot. So this is how you can define your service, and you can be sure that you're utilizing to a maximum extent. This is the same thing, taints and toleration. You can specify taints, and you can add this toleration here. I've used node selector, so you can have toleration here. Suppose you don't want any application to run on EKS managed nodes. So we at Cloudera have done it. We are only running Carpenter and daemon sets on EKS managed nodes. We have one node group, and every workload is now shifted to Carpenter based nodes. So we will be sure there's a difference between our EKS managed nodes. So both are very independently working. We don't really require EKS managed nodes apart from running Carpenter on it. So how do we do it? What's our solution, and what basic guidelines we follow? We follow a single node group policy. We don't have multiple node groups. So what it does, it helps you to uh, lesser the management of node groups. You don't have to worry about the node groups no more, because patching and AMI upgrade will be already handled by Carpenter for its nodes. We have all workloads running on Carpenter deployed nodes, and we manage it via Argo CD or any other platform we use. We have all things automated. We don't do anything manually. All the things are automated via IAC, and we have scripts even to generate the Helm files. So for us, Carpenter deployment takes no more than 30 or 1 hour maximum. And we have all the monitorings and alerts also set up. So Datadog, we use native Datadog APIs, native Datadog alerts to do that. So we have optimized solution, and I'm sure for our specific enterprise, we have a solid Carpenter solution. Now I want to present you a small demo just to show you how fast actually Carpenter scales the node. So suppose this is my deployment, and I have given replicas of 60. This is my replica 60. So you can see how big the replica is. And okay, now I'm applying this deployment. I will apply it and let's see what happens. So the deployment is created. Now let's see how fast Carpenter scales the node actually. So a concept called node claim. Node claim basically manages the life cycle of Carpenter. It takes data from EC2 class and node pool and makes into a single resource type. So you can see how fast the node started to scale. Within 15 seconds, within 10 seconds, a new node start to spin up. Right? But an interesting thing, you won't be seeing any pod scheduling. So the limit thing I was talking about right earlier, that you can set maximum limits. So Carpenter respects that and will not scale the instance because the limit I have set is lesser and you are over provisioning it, so it will not scale your instance. But what if I scale my instance down? Will it respect my limit? So for example, in this case, I'm trying to scale my replica down. Okay, my replica is scaled down. Let's see if it start to spin up pods or not. So I've checked the pods. So it start running the pods are now running. You can see the pods are running fine because I'm running in within the limit. If I remove the limit, the previous pods will also be running. Now let's see if the node claims are deleting or not. Because I've scaled down my pods, right? So let's see node claim should. So if you see here false, so it's actually decommissioning the node claims. See how fast it is. It is decommissioning this also. So within 30 seconds, 15 seconds, it start to decommission the nodes. It start to scale your nodes. So that's how fast Carpenter is. Carpenter takes 30 to 15 seconds to scale up your nodes, and cluster autoscaler traditional one uses 3 to 5 minutes to even scale up your nodes. And in total, cluster autoscaler takes 15 minutes. Scaling down with cluster autoscaler is even low. It takes 10 to 15 minutes to do so. But Carpenter, as you can see, it's 30 seconds. So you can see how much time difference it is. So I'm deleting the pod. You can see I've deleted my deployment. Now you can see more pods have started to get deleted. You can see another pod started to decommission. This false one started to decommission. So that's how fast Carpenter is. This demo was only to show you how fast Carpenter is and how powerful it is comparing to other autoscaling solution available. So I'm going to keep this demo short. Now I'm going to share with you. You might be wondering what's so special about Carpenter, how it does so many stuff. So there's a major use case for Carpenter. You might be wondering why I need to switch from cluster autoscaler to Carpenter. Give me a valid reason. So I'll give you it. We have consolidation policy set up. So when your instance is underutilized, not only it will club it to a single node group, sorry, single node, and it will change the instance type as well. So we have here a very utilized node, nothing wrong with it. We have partially utilized node, and these two are clearly underutilized, right? So what Carpenter does? So it clubs the two nodes into single node. Now you're running at a peak efficiency, and it will then reduce your cost because you're saving two nodes, right? Two heavy nodes, M5 nodes, you're saving, and it is clubbed into single node, and it even goes one step beyond. Suppose you have two M5X large instance running. Not only it will consolidate into a single node, it will also change the instance type. So you are saving money on the two nodes also, and also the instance type also. So you can see how much efficient it is, how much money you are saving, and it works on bin packing algorithm. So it tries to fit maximum instance in a single bin. So that's how you can save your cost. Now, another important thing I want to discuss about is drift. You might heard about Terraform drift, right? It's an headache, Terraform drift, but here it's not so the case. So for example, if I take Uh, so for example, if I take, uh, suppose in case you want to change, you have cluster running, you have M5 instance. Now you want to change something. You don't want M5 large nodes. Now, how will you change it? You might be thinking about blue-green deployment, create a temporary node group, shift the workloads. That is not the case here. So if you change the instance type here, Carpenter will detect the drift between your actual instance configuration and the configuration you previously have. So it will automatically starts to first increase the nodes for new instance type, terminate the older nodes, shift the workloads to new nodes, and then flush out the older nodes. So you will be shocked that it's so smooth that you won't even feel that your workload is migrated. So this is the mechanism Carpenter use drift to change an instance type. It constantly checks your manifest or whatever configuration you have, and it starts to change it based on that. Now, important feature I was talking about previously about upgrading and patching the AMIs. So how can you do that? So for example, you're currently running in 1.26 EKS cluster version, right? And you want to update to 1.27. So when you update the version, it will pick up the latest AMI from parameter store, AWS parameter store, and it will automatically change the AMI for you. And you can be sure that the new nodes that you are provisioning are with the latest AMI. So it's a zero touch and secure method. You won't be changing any instance type. You just upgrade the version and automatically the AMI will be upgraded for you. Now, what is the case that we have custom AMI? Because large enterprises have custom AMIs. Not they don't use AWS AMI. They use it, then hardened it, apply some patches, then deploy it. So Carpenter does have solution for that. So Cloudera personally, we are basically using this method, and we are using IDs or owner name. Also now we are using some Terraform outputs to do that. And it's very easy. So you can be sure every time that correct AMIs is applied on it. So there are two methods. You can use tag-based methods. You can use name or owner details for the AMI to manage it, or you can directly put the AMI. So if you put both AMIs together, it will not drain the existing AMI because it does not detect the drift. You have both AMIs correctly. But if you remove this and only have this, then it will start to produce nodes with new AMIs. It will produce new nodes, but it will not touch your older nodes. So it is very good for testing. You can test it on dev. You can have both AMIs running, and you can be sure that uh, there's no security hazard being deployed to environments. Uh, Also, we have at Cloudera logging setup already for Carpenter. So it's a very important part. Logging and monitoring is very important part for a complete solution. So you can spec the logs normally that you do for a deployments or daemon set. You can use kubectl deployment for Carpenter, and it will fetch you the logs. You can check it, troubleshoot it, but you can also send the logs to whatever logging platform you have, OpenSearch, Fluke, anything. Then you can use, it has open metrics and it opens up to port for Prometheus metrics. So you can directly use these metrics to create a dashboard, Grafana monitors, or anything. We have also monitor setup, alerting setup. So we'll be sure that when something misconfiguration happen, we are onto it very quickly. So I think logs and observability is a very important aspect of it as well. Now, a single thing I want to talk about, diving deep in the whole configuration as we have less time left now. So how you will be wondering how exactly Carpenter deprovisioning and scales up the node. So first of all, it will identify the candidates, right? So it will take the older node first, because you might be wondering, if I drain the newer node first, again, what happens if my newer nodes are drained? So specific services are placed into hazard. but it identifies the older candidate. It relaunches the replacement first. It drains your previous candidates and flush out the previous candidates, and now your workload will be running on newer one. So you should have pod disruption budgets set up in your service, because Carpenter respects your wish, and it depends on you how fast you want your nodes to drain. You can set up uh, pod disruption budget according to that, 2 3 1, so you can be sure that Carpenter respects them, and it will only drain the nodes the way you want it to be. If you want it fast, set the pod disruption budget accordingly. If you want it to drain slow, set it accordingly. So this is a standard workflow that Carpenter does to scale or drain or do anything to your nodes. And I highly recommend that you apply pod disruption budget to your applications if you have not already done, because it's a vital part of EK cycle. And one more thing, it is complete solution. All these things are packed into one solution. Carpenter does all of these things for you. So as I mentioned earlier, we personally have only one node group. We don't have to have a node group specification. Cluster auto scaling Carpenter does. Node termination descheduler, it does for you. And now there's a conclusion I want to share with you. It's a faster scaling decisions. It will make your scaling a lot more faster than it already is, as I showed you with the demo as well. It will give you instance type flexibility. You can choose from the instance type you want. You cannot choose it as well. Carpenter will choose it for you. Single node group management. You will need one single node group to manage your instance. Better resource utilization, as I mentioned, through consolidation process. So your resource is better managed. Cost optimization also let's talk about. It supports all type of workloads, ML, G2, P2, every type. And it helps in patching and upgrades. As I told previously, it upgrades to AMI and does the patching for you. So that's it from my side. And if you have any question, you can ask.
Yeah, what will trigger the activity actually?
What?
The Carpenter rebalancing, right? So if more ports will increase, it will automatically increase, right?
Yeah.
If I use a spot instances, so AWS need that spot instances, what it will act like? Carpenter, how it will behave?
So it will start spinning up your spot instance, right? So Carpenter has a good mechanism for spot consolidation. Also, if you have time, you can check the IAM resource. It's a spot termination handler. It contact with its event bridge also. So it launches large number of spot instance. Then it drains it. But you can be sure that your cron job, right? You spot instances already have another spot instance available. So even if your spot decommission, it will switch it to new instance. So you can be sure that spots are working fine and you won't face any disruptions in spot instance.
We are using PBD's majority at every 15 days, it's restarting. I mean, 15 days, it's recycling the one node.
Yeah,
and
node recycling, right?
Recycling.
We are recycling nodes per 30 days.
Okay.
So you will not notice the node recycling.
Yeah.
There's a policy that recycle nodes in particular hour. So if you apply that, it will automatically, as I mentioned earlier, spin up new nodes, drain your existing nodes, and then flush it, and all your instance will be in the new nodes. So yeah, you're correct.
That is mandatory, right? That is you're also doing.
No, it's not mandatory. It depends on you.
Okay.
It's not mandatory that will recycle the nodes. You have feature for it, but it's not mandatory. You can have same nodes as well.
Okay, thanks.
Hi, that was a good presentation. So I had question on the node eviction side. So
Node eviction?
Node eviction policy which you told. So how much time does it take for Carpenter to evict a node and then shift the workloads on the new node?
So in the demo I showed you, soon as you delete your application, right, it spins up new nodes. It starts spinning up new nodes within 15 seconds. Within 15 seconds, you will see a new node has started to come up. And it will take maximum 30 seconds to have an IP and everything assigned and create a single node. And it will not decommission your workload until a new node is first created. So you can be sure that your workloads are safe. When a new node is created, it drains node one by one. So one by one, it drains node, and that also depend on your PDP. It drains node one by one and starts shifting the workload to new nodes. So I can say you within 15 to 30 seconds, new instance come up.
Okay, okay. Also, this 15 to 30-second time, is it also a varying time depending on the instance type? Because you need to see the availability as well, right?
I was talking about triggering time. The actual migration will depend on your PDBs, your setup. If you set up large amount of PDBs, like 3 pods will always be there. So obviously it will take more time to shift your workloads. But if you set normal PDBs, like one PDB, always one node running, so it's usually faster. Like I can tell you within 1 minute, your couple of nodes can be
Yeah,
migrated.
right. We have seen a time of 2 to 3 minutes. So yeah.
Okay.
In last one slide, you mentioned about node termination handler.
Yeah.
Can you tell something more about it?
So node termination handler is simply the mechanism it uses to terminate your node, right? So even if you use cluster autoscaler or cube scheduler, it triggers whenever a node is decommissioned. It cluster autoscaler tells to autoscaling groups and it start to decommission the nodes. Carpenter does in backend for you. You don't have to like schedule descheduler. So node descheduling is work on descheduler as you're talking about. So that is managed by Carpenter. You don't have to worry about it. So all these things Carpenter packs for you. So that's what I'm talking about.
Hi, thank you for
Hello.
the great presentation. Yeah. So my question is, suppose I want a particular namespace should be, working with Carpenter, a particular namespace. So is there any native functionality from the Carpenter for a particular namespace that we can achieve?
Namespace, as I mentioned earlier, you can give affinity rules, right? So in the affinity rules, you can define if you want to have a deployment and you want deployment to have in a particular namespace, connect with another namespace. So you can provide some affinity, anti-affinity rules. Taint also you can provide. So you can use your native, whatever you do with Kubernetes, that you can do with Carpenter.
So basically, taint and toleration and
Taint
affinities we need to
toleration,
use.
node affinity, you can
There
use.
is no
node
native functionality or something from Carpenter, right?
No, namespace native functionality is not there.
Okay, okay.
You have to
Yeah.
that's the advantage. You can use the existing Kubernetes functionality in it with via YAML file or normal Kubernetes concepts.
Okay, one last question. Can we access the node groups that Carpenter is, provisioning for the controller or something?
You are provisioning it. Carpenter is not provisioning EKS managed node groups. One EKS managed node group you have to provision and you have total control over it. You can run Carpenter nodes in it and it's totally up to you. It takes, because we don't suggest your controller pods to run on Carpenter nodes deployed via Carpenter. What if something happens? So your whole cluster will be in shambles. So you need one single node group with 1 or 2 nodes to run your Carpenter pods in it. That's it.
And we can access the controller pod as well, right?
Yeah. You
And
can
we can
you
do
can
whatever
check
we
the
want.
logs. You can enter into it whatever you want.
Okay, thank you.
I think we have a couple of more questions.
Yeah, so I just wanted to know that it's how often is it polling for resources, the cluster resources, the EC2 resources. So it's trying to adjust itself constantly. So like, is it polling and how often is that a concern?
It constantly does that. It constantly tries to maintain the optimized state. So they have not given a timeline, but as soon as it finds it, it triggers it. Like as soon as it finds that resource can be optimized, it runs it. This doesn't have any schedule, but you can be sure every 1 minute it recycles everything
Okay.
and try to make your state cluster into a stable state. So it's a constant process. It's not like a fixed time it does it.
Okay. And I guess I assume that it works with other cloud providers as well and
Yeah.
standalone service. Okay.
Azure, GCP, everything. It works.
I think one last question. Yeah.
Just wanted to check with respect to the node provisioning here. So can node provisioning with the Carpenter can also be possible with the persistent volume, the backend storage?
With node provisioning with
Carpenter, along with persistent volume to
Persistent-
provision the, the static pods with
yeah, it's not related to Carpenter. Your service file is, you can do whatever you want with your service file. You can have persistent volume deployed with it. Anything. Carpenter doesn't control your service file. You can have your persistent volume. You can create it, your persistent volume, whatever you want, along with Carpenter.
Okay. Thank you.
Thank you. Thank you, everybody.
Yeah. Hello.
Yeah, hello.
Mukesh.
Yes, just one question. Yeah, if I create a placement groups, can it be attached to Carpenter?
Can you repeat? Sorry.
Placement group. If I have a placement groups, can a Carpenter attach the placement group to it?
Placement groups in what context? I didn't get
Like
the placement.
the rack, the specific rack, when it allocates the nodes, right? It should be specific on a nearby racks, nearby.
Yeah. It does it. Like whatever cluster autoscaler does it, it has placement groups, proximity groups. It respects all of it. So you can be sure that it respects that.
So how it ensures the availability? Like if a rack goes out of
Availability zone, as I mentioned earlier, in the node pool file, you can give 2A, 2B, 2C. In the node pool file, you will give the availability zones.
Okay.
Node
Means I mean to say,
pool.yaml.
if it goes out of storage, like if I have only 70 nodes available, if I need more, if it cannot satisfy the placement group policy, still it can expand.
Yeah, you can increase the limit, whatever your AWS limit is, it will go to maximum for that region. That's why I suggested limits also. So you can increase or decrease the limit. Limit is a feature like max available. So you can switch it to get your more instance or less instance.
Okay. Thank you.
Thank you.
Thank you so much, Harsh, and thanks for all the questions. If you guys have further, please reach out to him. I'll now request Dheeraj to move to further talk. He's from AWS.
So the topic I'm going to talk about today is log big or go home. So mostly it will be like how you can create a scalable logging stack using which you can monitor maybe Kubernetes cluster up to 1,000 nodes. So I'll share some stories on how we were able to scale up to 1,000 nodes in a Kubernetes cluster and how we were able to deal with the scalability problems in terms of logging stack. So I want it to be an interactive session. So feel free to raise your hands if you don't understand things in between or if you have any queries. And I would like your inputs as well when I'm designing the system. Okay, let's move ahead. So before I go ahead, I'll talk something about myself. My name is Dheeraj. I'm a senior software engineer at Amazon Web Services, popularly known as AWS. So there I work with the Aurora database team in the storage layer, which is like a multi-tenant storage system, which is used by many database engines. So our storage system is like not restricted to SQL or Postgres, but is even used by NoSQL and GraphDB databases. Apart from it, I'm a contributor and maintainer in the OpenSearch project. OpenSearch project, if you guys don't know, it is like the open source version of Elasticsearch. And there I manage the Kubernetes operators and Helm charts. So let's move on. So, right, everyone knows what is observability. Just telling about it, like it's an act of how you analyze the data and how you collect data from different systems. So there is a thin line between monitoring and observability. Monitoring, you are just doing monitoring. You are seeing the metrics and whatnot. But when I say it observability, it means that you are analyzing the logs. The logs are in a format that you can analyze and you can take out something meaningful from there. So what are the biggest challenges when it comes to containerized applications? Like a single pod, it contains like 20 metrics if it's a very simple application, and there are 30, 35 metrics which are by default present. So each pod, it's containing 55 metrics, and consider the scale of 1,000 Kubernetes cluster. So you can multiply it. So that's the amount of metrics you get. And if you're not able to capture those in a way which is understandable, it is very difficult. So this is a famous Shibuya crossing in Tokyo. So resources in this containerized world, they are similar to like this. They are ephemeral and they are dynamic in nature. So it's very difficult to catch the current state and observe it. Now, people back in before 5-7 years, we used to use legacy technologies. Then someone told that, okay, Kubernetes, once you move to Kubernetes, every problem is solved. But that's not the case. Migrating to Kubernetes, I am damn sure that many of you here have had tough times migrating to Kubernetes. So there are many important things, biggest challenges which comes in. First is like large scale. So if it's a very huge cluster, you'll have a lot of volume of signals. So let's move on. So during the design, which I'll be doing, I'll be using mostly these technologies, but I'll talk about different patterns as well. Apart from the pattern we used in scaling that 1,000 node cluster, there are some other patterns as well, which we can use. OpenSearch, FluentD, Jaeger, Grafana, Prometheus, OpenTelemetry. So this is the first logging pattern where you use a dedicated logging container or a dedicated monitoring container. So here you are running a separate container just for monitoring and for logging purposes. For example, if these are your Kubernetes nodes, either you have your Grafana or your whole Prometheus setup, which is completely decoupled from your application layer. The next logging pattern is where you are using the whole platform, like be the ELK platform, that is Elasticsearch Log Kibana platform. So here also it is something similar, but there are two options here. One option is that you might not run this whole ELK stack in your Kubernetes cluster. The other option is that you run everything in the ELKs, in your Kubernetes cluster itself. So I think ELK also has Kubernetes operators and all, by using which you can run it. The third logging pattern is when you want to use a distributed tracing system. So for folks who are not aware about what is a distributed tracing system, so it is mostly like, suppose you're trying to order something from Swiggy. So in Swiggy, there'll be multiple microservices and the request goes through various microservices. Now you want to trace the request from the mobile application to the microservices, maybe which place the order. So the entire trace of the request can be handled using this distributed tracing system. So this is one logging pattern. The fourth logging pattern is when you can use a service mesh. So when you use a service mesh, like either Istio or a Linkerd, so it's something like it sits on top of your application, and whatever requests are coming in, whatever requests are going out from the service, so it is able to do all the metrics, logging, and monitoring as part of that. Any questions still here, like the four logging patterns and the challenges? Okay, I think we are following good. So I don't want it to sound like a monologue. So let's see what were the 1,000 node cluster major problems. So remember these 3 points, 1, 2, and 3. I'm going to talk about each of them and how each of the problems were handled. First was the data volume, like there'll be a lot of data, be it metrics or logs. Next is the performance. Like when we started off, there were developers telling, okay, my application logs are taking a lot of time. Your service logs are coming up okay. Because it was a multi-tenant cluster, so there were multiple microservices using that cluster. So this was a very critical thing. We wanted to ensure that the performance of the logging is very good. And third, which is very important in today's world, is being frugal. So whenever you are doing any design, right now, one of the design principles, which is very important, is apart from performance, scalability, everything, you need to be frugal. So you need to be frugal when you design it. So this is the stack. I'll also be showing some demo. So at one side, there's a pull mechanism. The other side, there's a push mechanism. So let's see now. So node 1, 2, 3. So similarly, we have like many nodes in the Kubernetes cluster. We have installed FluentD, which runs as a daemon set in the node itself. And what it does, it will ingest logs to OpenSearch. Now, why we have used OpenSearch is we wanted to utilize the functionality of complete search, full text search, so that it's very easy for anyone. Even tomorrow, if a developer joins our system, he can check the logs and it will be very easy for him. The third thing we have used is OpenSearch dashboards. Now, the reason for it is we wanted to visualize all the logs. The other side of the spectrum, if you see, it is a dedicating metrics monitoring thing. Like we have a Prometheus server, which is now pulling all the metrics from our Kubernetes cluster and is showing in a Grafana dashboard. Now, the only reason why we have two things, one is logs and metrics, is we wanted to keep things decoupled and just for performance sake. So I'll show a quick demo before I answer all the 3 questions related to the slide which I showed before. So let me show you how it will look like. So first I'll show Grafana. Okay, 1 second. Yeah, so this is how standard Grafana dashboard look like. So basically, whatever metrics it is pulling, the Prometheus server is pulling, it will be displayed here, like how many kubelets are running, how many pods are running. Also, this is not the 1000-node cluster. This is just a local cluster which I'm running on my personal laptop. So in Grafana, basically, you can create multiple kind of dashboards based on the requirement. This is just a system dashboard of a Kubernetes cluster, but you can even create dashboards based on the application metrics that you have. The other thing now is like the text search, which I was talking about. So here I'm running some containers in my Kubernetes cluster. Now, if you want to check logs, it's very simple here. Like what I have done is every logs which is getting emitted, it is creating indexes. So for example, my application logs of service A, it is creating one index in my OpenSearch cluster. Now, if you want to query that, I can just query using the index. Now, creating indexes in OpenSearch cluster based on the logs also requires some bit of design. Now, how we have done is that for every service level and for every service at the application level, we have tried creating indexes so that it is scalable for us. And how we are being frugal there, I'll talk later, but I'll explain here that for searching now, things become very simple. For example, if I want to see how my logging agent is performing, I can just type maybe Fluent or something like this. Then it will, okay, 1 second. Just a second. Yeah, if I type Fluent, it will show me all the logs related to Fluent. So grepping like we do in our day-to-day systems, it becomes very easy when we are using OpenSearch dashboard. Now, let's move on. Think. Okay. Yep. So now the most interesting part, like the first problem which I talked about was, if you guys remember, was data volume. Okay. So now how we tried to handle the data volume problem was we routed the logs. So in FluentBit and in FluentD, there is an option by which you can filter and you can route logs to different clusters. So first of all, what we did was we sharded all the nodes and we created OpenSearch clusters based on the node numbers. For example, 10 or 15 nodes are having one OpenSearch clusters. Then 20 to 35, they are having one OpenSearch clusters. So for the whole 1000-node cluster, Kubernetes cluster, there were multiple OpenSearch clusters which were handling a subset of logs. Now, FluentBit was configured in a way that if service A is running and service A has some application logs and then some service logs, then we are creating different indexes for it. Now, the third point, if you remember in the slide, was how I'm being frugal. You will tell me that this guy is just creating clusters and all, and then he's talking about frugality as well. So how we are doing this is the third point, the data retention and cleanup. So we make sure that the indexes, they are auto-deleted and all the logs and everything, they are archived in some blob storage. It can be S3 or anything, any cloud-native storage. So once the indexes, they are getting deleted, so all the indexes lifecycle we are managing. For example, if we know that these kind of logs are not required to be persisted maybe 2 or 3 days in that OpenSearch cluster, we don't need it. We just put them to our archive solution S3. And from there, we can easily query whenever we need it. Now, the other thing I was talking about was performance. So now the performance part is the multiple index and index sharding, which I was talking, like how I am trying to create many indexes as possible. And in OpenSearch, we have an option, right? You can create primary shards, multiple primary shards there. Now, we need to reach an optimum number of primary shards. So if you don't reach an optimum number of primary shards for a particular index, then it will lead to performance issues. So for example, the log fetching time is more. So that means definitely that the shard count is less for you. But you shouldn't do that also that, okay, for my index, I'm just creating the shards and all, like multiple shards and everything. So that will increase the cost for you. So that is one thing, that you need to configure multiple indexes. You need to use index sharding. and have indices for different types of logs. So one is log routing, one is index sharding, and one is data retention and cleanup. So this is the way mostly how we scaled this 1,000 node Kubernetes clusters. Any questions? So I kept additional time just those so that we can discuss.
Siding on the timestamp or siding on some ID in the log, or siding on some transaction ID. What particular line item you are doing index sharding?
When I say sharding, one shard is just on the index level. So OpenSearch uses Leucine index. So if we increase the number of shards, that is one performance level sharding. The other thing which I was talking about is you create different indexes for different kind of logs. So for example, if you have application logs, you create a different index. If you have some daily logs, you create a different index for it. Weekly logs, you create a different index for it. So this way you can optimize the performance.
But all the log, it is coming to the open search in the general.
Yes.
Then there you have written some algorithm to identify the log, like coming for the different containers, different pod, or how you identify that different types of log it is coming, then creating the index.
Correct. So what happens is we have FluentD, which is installed in each of the nodes, right? So
Yeah.
now there we have filtering options. Like for this particular type of logs in that pods, go to that OpenSearch cluster. So that algorithm is written as part of FluentD, and we have an external workflow now which is running on the client side on the dev machine, which helps them identify, okay, this is the cluster I need to check the logs on, if that was your question.
Yeah, just to understand that this is good for this open search. Same mechanism you have done for the Prometheus server, like same way it is doing that way.
Can you come again?
Like how it is identified this log, like in the Fluent, you had written that identifier type. Similar to that where that Grafana is doing pull. There also you have written some type of identifier for the log.
No, in that case, that we are just using for metrics. And as of now, with the current scale, we haven't seen any scalability issues in terms of metrics. There we have just one, like multiple Prometheus servers are there, but we have just one dashboard which is like capable of doing all the metrics. We have not seen issues with metrics. We were just seeing performance issues with logs. And that's why we all did all this sharding, all this scalability issues and performance issues.
One more question, like when you are given the presentation, can you open the slide? Like how much cluster you are having there? Like it was showing one machine only, but it was node, it was showing one node, but cluster it was not showing. How much cluster you have got in that?
It is just one EKS cluster.
One cluster.
One Kubernetes cluster, 1,000 nodes. So that's what I was explaining, like in the problem as well. It is just one EKS cluster and 1,000 nodes in that cluster.
Oh.
So we needed that one EKS cluster only. So that's the reason we took it.
Okay. Thank you.
Yeah.
You said that there are multiple OpenSearch clusters, and you have like set like certain number of Kubernetes nodes go to this cluster, etc.
Correct.
Now, if I have an application or a deployment whose pods are spread across all the nodes of the Kubernetes clusters, and their logs are going to different OpenSearch clusters, how do I search across those OpenSearch clusters, because it's still the same logical application, right?
Yes, right. So in the case of the FluentD, which is sending the logs, it is ensured. We have written some custom operators there, so which ensures that when an application is spread across multiple nodes, all of them will go in a single OpenSearch cluster. So it is ensured that every application which is running in the whole Kubernetes cluster, they will definitely go to one Kubernetes, one OpenSearch cluster. So the whole project is open source as well, the whole pattern of how we have done it. So I'll share it.
Yeah, so I had question on the hosting solution for OpenSearch. So you are hosting it as a Amazon managed OpenSearch service, or is it kind of on Kubernetes server?
Yeah, so that really depends on how you want to do it. So if you remember the logging pattern 4, logging pattern 2, so it is similar to how we have done it. But in our case, we have installed OpenSearch on Kubernetes itself. So we have used Helm charts to install OpenSearch on the Kubernetes cluster itself.
Okay. So thing is with OpenSearch, the issue which comes up is scaling. And let's say you have a burst of pods, the pod scaled up horizontally.
Yes.
And the OpenSearch benchmarking which we have done is on certain number of load. So like how to handle such bottleneck situation in this case?
Yeah, in this case, how we handled was we created multiple OpenSearch serverless clusters is how we handled it.
Okay, so you created multiple clusters based
That-
on the load.
Based on the load. And that's why we are getting better performance.
Any numbers you have in terms of cost, like
Yeah, it's very difficult because there were a lot of applications which are running.
Right,
And
because
it's just one AWS account, so it's very difficult to give the exact numbers on the cost. But overall, with the management of the index lifecycle, we were able to optimize the cost because we are not at runtime. At any point of time, we are not storing a lot of data in the OpenSearch cluster. And that is where we are saving money.
Okay, and now coming to the indexing part, you said indexing is kind of dependent on shards. So what kind of sharding policy you followed?
When you say sharding policy, you mean the indexing I was talking about is how many primary shards you are creating when you are creating that index.
Yeah.
So we make sure that we create not a lot, but an optimum number of shards. For example, for one hour of our application, we have even created 6 to 7 shards because we know it's a very important application and there are a lot of developers accessing logs from there. So based on that number, we create the number of shards so that the performance is not impacted, but you still get the logs from the Kubernetes cluster.
Okay, okay. I was asking from the point of view, like, did you explore the part that the number of shards can be kept equal to the number of CPU cores you have because the sharding process happens at CPU level.
Right.
And the
right.
index search happens at the CPU level.
Correct. But it was not working well for us in terms of performance.
Okay.
We were seeing like CPU spikes and we were seeing search latencies when we did that. So initially we had kept the number of shards at constant. It was constant for all applications and it was increasing based on the CPU. But after that, we thought that for certain applications, we need to manage this dynamically. So now we create the number of shards based on the application logs.
Based on the upload. Okay, thanks.
So is this architecture for Aurora or? No, this architecture is not Aurora. So in Aurora, we don't use directly use Kubernetes cluster. But yeah, one of our applications, we have used this kind of architecture. Okay.
Hey, I'm more interested in the DB model used by OpenSearch. Does it use an append-only document database, or what it uses?
Can you say once again?
So what's the DB model used by OpenSearch?
It's a document-based database. So every index, you can consider it as a database in the world of RDBMS.
Okay. So, and does it do regular compaction itself? Compaction.
Compaction.
Yes.
What do you mean? Maybe I'm not aware. Compaction.
So how does it handle duplicates in terms of compaction and to improve faster search?
Yeah. That is so it is based on Lucene index. So Lucene index in very layman terms, if I explain you, if you know the edit distance algorithm, the day-to-day problem which we solve, like you have given 2 words and you want to create a new word. So you want to find out like how many letters you need to change in order to form that new word. So based on that algorithm, only Lucene works. And Lucene is basically the main core part over which the whole OpenSearch is built. So it is built that.
So I read that you are one of the open source maintainers for OpenSearch, right? Yep. So you're fairly comfortable with all the complexities of actually like fine-tuning it with regards to sharding, with regards to indexing, with regards to cluster management, scaling up, scaling down, versus like there are at scale companies are now moving towards either low-key or towards, in some cases, ClickHouse as well for logs, right? So have you or your team done a comparative analysis? Because A, from a management, and B, from a cost perspective, it makes a significant difference, and it also hyperscales to the scales or even higher than OpenSearch, right? So have you done a comparison on those, and is there a recommendation that you're going to share over?
Yep. So when you say about the Grafana and Loki based systems, it is almost equally scalable, and I'll say more scalable when it comes to nodes. That's correct. But the only thing which was missing here and which we wanted was the full text search functionality. That is not there. And we needed it based on the operators which access our logs. So that's the reason we kept it. So that was the major trade-off we did it. So it was more on a use case perspective we have seen. But from a cost perspective, when we analyze the cost, it was around 13%, which OpenSearch, the whole OpenSearch setup, was costlier than Grafana Loki system. So it's 13%, 1-3. This was the trade-off we made. So the major cost saving is the data retention thing that we are doing, the archival and everything. Yes, yes, we are keeping the data in cold store. The last part, if you see. So this is the part where we are saving the cost. And this I would highly suggest, if you are storing logs in any central store, just try to archive it whenever possible. You don't need logs of like 1 year, 2 years sitting on the same cluster. And this is one of the things which we had seen in our team. Okay.
Yes, hi. So I was just wondering if is there any concerns regarding, bottlenecks in logging performances? Like when you do cleanups, for example, since let's say you have so many indexes you clean up, you might have issues with performances. So do you use certain configurations? Have you experimented with them, like replica, primary replica configuration, and there's so many others? Can you just talk about that a little bit?
Yes, yes. So are you talking about the performance when we are sending the logs to the OpenSearch cluster from Kubernetes? Or you're talking about the performance when we are accessing the logs from the cluster?
I mean, yes, even in terms of writes, reads, maintenance, cleanup.
Okay, okay.
Just
Yeah.
touch upon
Yeah, I
all
can
of
touch
that.
about it. So basically what we first did was there were multiple experiments we ran. So what we did was we created a dummy application that was creating a lot of logs for us. And then we tried scaling. Then we hit into a limit that our search latency was spiking a lot. When the shards were caught, and someone asked here that why didn't you keep the shard constant? So we kept the shard constant. That was a very standard thing, that whatever indexes you are creating, keep the number of shards as constant. Then we saw high CPU spikes. Our cluster were facing search latency and all. And then we kind of tried fine tuning the first part. The first part as in the place where we are sending the logs. So how to fix those? So in that cases, the replicas, we have kept it very less. We are, you can say we are trading off a bit on that front. But on the primary, we have increased the number of primary shards there. The other thing which we did was on the sharding of the OpenSearch clusters. Like previously, for the whole 1,000 node clusters, we were using just 3 OpenSearch clusters to start off. And now we have like 4 more. So approximately we have 9 to 10 as of now in production. So with 10 OpenSearch clusters, we are able to kind of handle the whole load. So this is how we kind of fine-tuned. So first we started with like a suboptimal configurations, and then slowly, gradually we scaled up. So it's most of I'll say a learning in production. Because once we started migrating to Kubernetes, it was easy as we felt like seeing everything, but gradually it was a bit tricky. Okay, I think that was all. So what I'll suggest is, if you log things well, your life will be easier, at least if you are any software engineer, developer, anyone. If logging is something you neglect, then your mean time to detection, which is very important in software engineering, and the mean time to resolution, which is also very important. The time it takes to detect an issue and the time it takes to resolve an issue all depends on observability, which is logging and monitoring. Yeah, that's all. Thank you.
Thank you so much, Dheeraj. Thank you so much, Dheeraj, Harsh, Priya, and Avanish for the amazing presentation. And thanks to you all.